Thank you for listening. This course was created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional podcasts, books, newsletters, and cool merchandise await. Let's get started. Artificial intelligence relies heavily on cloud infrastructure as its foundational layer. This infrastructure is composed of compute, storage, and networking resources, all orchestrated to support both training and inference at scale. Compute resources provide the raw processing power, storage ensures that datasets and model checkpoints are reliably housed, and networking enables secure connectivity between components. Modern AI systems depend on hyperscale cloud providers that can deliver these resources elastically and on demand. The relationship is structured around a shared responsibility model, where the provider secures the underlying hardware and physical facilities, while customers are accountable for securing their applications, data, and configurations. This dynamic makes cloud infrastructure both a powerful enabler and a potential source of risk. Understanding its components and responsibilities is the first step toward building secure and resilient AI systems that can withstand both technical and operational challenges. Compute is the engine of AI cloud infrastructure. Graphics processing units, or GPUs, and tensor processing units, or TPUs, accelerate the linear algebra operations central to model training and inference. High-memory instances provide the capacity required for massive parameter sets and large batch processing. Distributed clusters connect many of these instances together, enabling parallelization that makes training trillion-parameter models possible. Autoscaling mechanisms add flexibility, dynamically adjusting the number of active instances to match workload demand. While these capabilities provide incredible performance, they also introduce risks. Poorly secured clusters can be hijacked for illicit use, and mismanaged autoscaling can lead to runaway costs. Secure configuration and monitoring of compute resources are thus as important as raw performance, ensuring that the immense power of cloud compute remains under organizational control. Storage is the backbone that feeds these compute resources with data. Object stores, such as Amazon S3 or Google Cloud Storage, hold massive training datasets in scalable, cost-effective formats. Block storage is used for high-performance needs, such as storing model checkpoints during iterative training. Caching layers improve inference speed by keeping frequently accessed embeddings or models close to compute. Encryption requirements apply to all these forms of storage, ensuring that sensitive data remains protected at rest. Yet storage also represents one of the most common sources of risk in cloud AI. Misconfigured buckets can expose entire datasets publicly, and poorly managed permissions can allow unauthorized access. Strong encryption, clear access controls, and routine audits turn storage from a liability into a reliable, governed component of AI infrastructure. Networking forms the connective tissue of cloud-based AI systems. Secure virtual private cloud, or VPC configuration segment workloads into protected spaces, reducing exposure. Private connectivity options, such as dedicated interconnects, ensure sensitive data avoids the public internet. Firewalls enforce rules about which services can communicate, while segmentation strategies prevent lateral movement in case of compromise. Together, these controls define the secure pathways along which data flows between compute, storage, and clients. In practice, the network layer is both a shield and a highway. It must be open enough to enable training at scale, but secure enough to prevent external intrusion. Misconfigurations here are particularly dangerous, as a single exposed endpoint can become the entry point for attackers. Secure networking is thus essential to protecting AI systems in the cloud. The shared responsibility model underpins every aspect of cloud AI security. Providers are responsible for safeguarding the infrastructure fabric, the data centers, the physical machines, and the core virtualization layers. Customers, however, bear responsibility for securing their applications, configurations, data, and identities within that fabric. Clear boundary definitions are vital to avoid gaps where neither party enforces security. For example, While a cloud provider ensures that hardware is patched against processor vulnerabilities, it is the customer's duty to configure IAM roles correctly to prevent unauthorized access. Failing to understand this division leads to misplaced assumptions and unmitigated risks. The shared responsibility model requires customers to act not as passive consumers of cloud services but as active stewards of their slice of security. Cloud threats specific to AI. I highlight how this shared model can fail in practice. Misconfigured buckets expose sensitive datasets, sometimes discovered by adversaries through automated scanning. Exposed endpoints, such as unsecured inference APIs, provide attackers with footholds for abuse. Tenant isolation failures, though rare, pose risks in multi-tenant clouds, where vulnerabilities could allow one customer to access another's resources. Resource exhaustion occurs when adversaries intentionally consume cloud capacity, either to degrade performance or drive up costs. These threats demonstrate that the cloud is not inherently safe. It requires vigilance and disciplined configuration. For AI systems, where workloads are complex and data is sensitive, the stakes are particularly high. Strong governance and continuous monitoring are the best defenses against these ever-present risks. Infrastructure attacks in cloud environments target both the scale and the complexity of AI systems. Denial of service campaigns can overwhelm distributed clusters, preventing models from training or serving inference. Privilege escalation within the cloud allows adversaries to take over higher-level roles, granting them access to sensitive datasets or administrative controls. Exploiting vulnerabilities in cloud services or third-party dependencies can provide footholds for deeper compromise. Lateral movement across tenants, though rare, is particularly concerning in shared infrastructure because it undermines the trust that multi-tenant environments rely on. These attack patterns reveal that even hyperscale providers are not immune to the fundamental realities of cybersecurity. For AI workloads, which are resource-intensive and often run continuously, the impact of such attacks can be devastating, halting progress and consuming budgets. Defenses must anticipate both targeted and opportunistic threats. Identity and access management is often described as the first line of defense in cloud AI environments. Proper configuration of IAM roles ensures that only authorized users and services can interact with resources. Least privilege policies further reduce exposure by granting only the permissions strictly required for a task, limiting the blast radius of compromise. Credential rotation ensures that long-lived secrets do not become permanent backdoors, while multi-factor authentication raises the bar for unauthorized access attempts. Misconfigured IAM, however, remains one of the most common causes of cloud breaches. For AI teams, strong access management is essential, as the resources they control, datasets, models, and training environments represent both high value and high sensitivity. Treating identity as a cornerstone of infrastructure security is not optional. It is the foundation. Encryption practices extend this foundation by protecting data across its lifecycle. At rest, encryption secures datasets, checkpoints, and logs stored in object and block storage, ensuring they are unreadable without proper keys. In transit, encryption shields information as it moves across networks, whether between clusters, storage systems, or external clients. Key management practices, such as centralized vaults and automated rotation, prevent weak or stale encryption from becoming an Achilles heel. Some providers now offer attestation services, which cryptographically verify that workloads are running on trusted hardware with approved configurations. These practices matter deeply in AI, where sensitive personal data or proprietary training sets are common. Encryption transforms raw infrastructure into a trustworthy platform, making it possible to train and deploy with confidence that information remains confidential. Monitoring and logging convert infrastructure activity into actionable intelligence. Collecting audit logs provides detailed records of who accessed what, when, and how, forming the basis of accountability. Anomaly detection systems analyze usage patterns, flagging deviations that may indicate abuse or misconfiguration. Correlation with Security Operations Center systems allows cloud activity to be evaluated alongside enterprise-wide signals, strengthening detection of complex attack campaigns. Forensic replay capabilities enable post-incident investigations, reconstructing the sequence of actions that led to a breach or outage. Monitoring is especially critical in AI contexts, where workloads may be opaque or automated. Visibility ensures that surprises, whether errors or attacks, are not invisible. Logs and alerts create the transparency needed for trust, making monitoring a continuous partner in both operational resilience and governance. Resilience practices ensure that cloud-based AI workloads survive disruptions, whether caused by accidents, attacks, or natural disasters. Multi-region redundancy distributes models and datasets across geographies, ensuring that failures in one region do not stop operations globally. Disaster recovery planning establishes procedures for restoring services quickly under stress, while failover testing validates that these plans work in practice rather than just on paper. Backup validation ensures that stored copies of data and checkpoints can be restored when needed, preventing the false comfort of unusable backups. For AI systems which often underpin critical decision-making, resilience is as important as security. Together, these practices ensure that organizations not only withstand attacks, but also recover gracefully from the inevitable disruptions of large-scale operations. Compliance overlays these technical practices with legal and regulatory obligations. Regulatory alignment ensures that the use of cloud AI adheres to data protection laws, industry mandates, and sector-specific requirements. Evidence collection supports audits by demonstrating that controls such as encryption and access management are consistently applied. Sector-based mandates, whether in healthcare, finance, or government, may impose stricter rules for handling sensitive workloads. Audit trails, built from monitoring and logging, provide verifiable records of adherence. Compliance is not merely a bureaucratic exercise. It is a mechanism of trust that reassures customers, regulators, and partners that AI systems are being operated responsibly. By weaving compliance into infrastructure management, organizations transform obligations into opportunities for stronger governance and clearer accountability. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Zero Trust in Cloud AI builds on the principle that no service or workload should be implicitly trusted simply because it operates inside the same environment. Each interaction between compute, storage, and networking must undergo continuous verification. Microsegmentation of workloads prevents broad access, ensuring that even within a virtual private cloud, services only communicate with explicitly approved peers. Continuous verification means that tokens, certificates, and permissions are validated at every request rather than assumed to persist safely. Adaptive enforcement raises security levels dynamically in response to anomalies, such as unexpected surges in traffic or suspicious access attempts. In practice, Zero Trust transforms cloud AI from a network-centric model of trust to a context-aware model where access is earned continuously. This philosophy ensures that compromise of one component does not automatically cascade into systemic breaches. Infrastructure as Code, or IAC, extends security into the design and deployment of cloud AI environments. Version templates capture the desired state of resources, allowing infrastructure to be reviewed and audited just like application code. Automated scanning tools analyze these templates for misconfigurations, catching vulnerabilities before they are deployed. Policy enforcement pipelines block unsafe changes, ensuring that violations of security standards are never promoted into production. Rollback mechanisms allow rapid recovery if a new configuration proves harmful, minimizing downtime and exposure. For AI systems, where infrastructure is complex and dynamic, IAC provides both efficiency and assurance. It reduces human error, improves consistency, and embeds governance into the very process of building environments. This proactive approach transforms infrastructure from a potential source of risk into a controlled and predictable foundation. Provider security services offer organizations pre-built capabilities that enhance the protection of AI workloads. Managed encryption options simplify the process of securing data at rest and in transit, often integrating with provider-run key management systems. Security posture dashboards give visibility into misconfigurations, vulnerabilities, and compliance gaps across accounts and services. Automated threat detection systems analyze activity patterns to identify suspicious behavior, such as privilege escalation attempts or brute force access trials. Compliance automation tools help organizations meet regulatory requirements by generating evidence and monitoring adherence in real time. These services represent the advantage of hyperscale providers. They can deliver security capabilities at a scale and sophistication difficult for customers to build alone. Leveraging them wisely allows AI teams to focus on their core mission without neglecting essential defenses. Operational best practices remain critical, even when advanced tools are available. Regular patching cycles ensure that both provider-managed and customer-managed resources remain current against known vulnerabilities. Vulnerability management programs prioritize remediation based on severity and exposure, reducing the risk of exploitation. Separation of duties prevents any single administrator from holding unchecked power, minimizing insider risk. Privileged access reviews regularly audit who has elevated rights, ensuring that permissions are still justified and revoking those that are not. In cloud AI environments where resources are valuable and often shared across teams, these practices provide discipline and accountability. They remind organizations that security is not only about technology but also about the processes and people who operate it. Metrics for cloud AI security provide measurable indicators of posture and progress. Tracking the number of misconfigurations detected over time highlights whether IAC and governance controls are effective. Measuring incident response timeframes shows how quickly teams can detect, analyze, and contain cloud-related threats. Compliance coverage scores quantify how thoroughly regulatory requirements are being met, providing a benchmark for audits. Resilience availability metrics reflect the system's ability to maintain operations during disruptions, whether from technical failures or external attacks. These metrics transform cloud security from a matter of assumption into one of evidence. They enable leaders to allocate resources intelligently, prioritize improvements, and communicate risk in quantifiable terms. In doing so, metrics make security a continuous process of monitoring, adjustment, and validation. This strategic role of cloud security in AI cannot be overstated. Secure infrastructure enables enterprise-scale AI by providing confidence that workloads can scale safely across geographies and industries. It reduces systemic risk by ensuring that failures or breaches do not propagate across tenants or services. It protects sensitive workloads, whether personal health information, financial data, or proprietary intellectual property, from compromise. Most importantly, it provides the foundation upon which advanced AI security techniques, such as sandboxing, plug-in controls, and provenance tracking, can be layered. Without secure cloud infrastructure, these advanced measures have little to stand on. Thus, cloud security is not just an operational concern, but a strategic imperative. It is the bedrock upon which trustworthy, compliant, and resilient AI systems are built. In conclusion, cloud and infrastructure security for AI is not just about technology stacks. It is about designing environments where sensitive data and powerful compute resources can operate safely at scale. We began with the definition of AI cloud infrastructure, showing how compute, storage, and networking provide the foundation for training and inference. Each of these components brings both capabilities and risks, from misconfigured storage buckets to exposed endpoints. The shared responsibility model reminds us that while providers secure the underlying platform, customers must diligently configure and manage their own environments. Recognizing threats unique to AI, such as resource exhaustion or tenant isolation failures, helps organizations prepare not just for generic cloud risks, but for those amplified by AI's scale and complexity. Resilience practices further strengthen trust in cloud AI deployments. By planning for redundancy, failover, and recovery, organizations ensure that even when disruptions occur, services remain available. These safeguards make cloud infrastructure dependable, not only under normal conditions, but also during stress. Compliance overlays this with accountability, demonstrating to regulators and stakeholders that systems are not only functional but also responsible. With audit trails and evidence collection, compliance practices turn infrastructure management into a mechanism for building trust. This layered view, combining technical, operational, and legal considerations, shows that cloud AI security is a multidimensional effort requiring both precision and foresight. Zero trust principles adapt naturally to cloud environments, requiring verification at every interaction between services. Combined with infrastructure as code practices, they create environments that are not only secure but also consistent and auditable. Provider security services add another layer of assurance, offering organizations capabilities they might struggle to build on their own. Operational best practices and careful monitoring ensure that these tools are not taken for granted but integrated into a disciplined security culture. By measuring effectiveness through clear metrics, leaders gain visibility into strengths, weaknesses, and areas for investment. These elements together form a framework where AI systems can operate safely and confidently at enterprise scale. The strategic role of cloud security becomes even more apparent when viewed as the foundation for future innovation. Advanced techniques like secure plugin execution, model provenance tracking, and automated policy enforcement all depend on reliable infrastructure beneath them. Without resilient and secure cloud platforms, these higher-level controls cannot function effectively. Cloud security thus becomes a multiplier. By strengthening it, organizations enable all other layers of AI governance and defense. It ensures that AI can be developed, deployed, and scaled without introducing unacceptable risks to the enterprise. As AI becomes central to competitive advantage, cloud security becomes central to AI itself. Looking ahead, the importance of key management and encryption will rise as organizations handle increasingly sensitive data in AI pipelines. Encrypting at rest and in transit is no longer sufficient. Attention must shift to how encryption keys are generated, stored, rotated, and verified. Attestation and confidential computing will further enhance trust, ensuring that workloads are not only secure but also provably so. This next stage builds directly on the cloud security principles discussed here, showing that progress in AI security is sequential and cumulative. Each layer enables the next, creating a defense-in-depth strategy that is both robust and adaptable. As we transition to the next episode on keys and encryption, the journey comes full circle. Cloud and infrastructure security establishes the environment, but cryptography provides the guarantees of confidentiality, integrity, and authenticity that underpin trust. By mastering cloud controls, organizations prepare themselves to manage keys responsibly, implement strong encryption, and align with regulatory demands. Together, these measures transform AI from a promising technology into a dependable enterprise asset. The lessons of this episode remind us that security is not just an add-on, but a design principle, one that begins at the infrastructure level and extends upward into every part of the AI lifecycle. Thanks for tuning in to Bare Metal Cyber, your trusted source for cybersecurity educational materials, news, and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.